Okay, in this video we're going to solve another problem from Neaman Microelectronics. This one is problem 4.70 from the textbook problems. Again, we're going to skip the analysis of finding R1 and R2. They're not going to impact the gain in this particular case, but we will need to find RS1, RD1, and RS2. It tells us that the current through ID1 is 0.1 milliamps and the current through ID2 is 0.3 milliamps, and it tells us the source to drain voltage and drain to source voltage that it desires in both cases, and initially gives us what the source voltage is for stage 1. So with that, we can find values. So it tells us that the source voltage for the first stage is 0.6 volts. And it further tells us that it wants the drain to source voltage to be 1 volt, which means that the drain voltage of the first stage needs to be minus 0.4 volts. Now it's already provided a current, so all we need to do is use the voltage across those resistors to find their values, given that the current is given. So RS1 is 1.2 volts divided by 0.1 milliamps, or 12 kiloohms. RD1 is equal to 1.4 volts over 0.1 milliamps, or 14 kiloohms. For the second stage, we need to find the overdrive voltage. Here, the overdrive voltage is equal to 0.11 volts. We know that VOV2 is equal to VGS minus VTH in. We can say that VGS is equal to 0.51 volts. Now we further know that VG is equal to minus 0.4 volts, and this means that VS is equal to minus 0.91 volts. All right, now we know the voltage across RS2, and we know the current that we want through that transistor, so we can find the value of RS2. RS2 is approximately equal to 0.9 volts divided by 0.3 milliamps, or approximately 3 kiloohms. All right, so we now have all the resistor values. We need to find the GM values for the transistors quickly. GM of the first stage is equal to square root of 2 ID times K prime times W over L. This is 0.4 millisiemens. GM2 is equal to 2ID over VOV. This is equal to 5.4 millisiemens. All right, in this case, we don't have any capacitors to worry about. We don't have a voltage division at the input because the source voltage doesn't have a resistor in series with it. So we have the input on the gate and the output on the drain of M1. That's a common source amplifier. And the input is on the gate and the output is on the source of M2. So this is a common drain amplifier. So we can now write our voltage gain expression. All right, So we don't have any capacitors shorting the source resistances in this particular case like we did in the last example. And we also note again that the lambda values given are equal to 0, which means that the R naught for each of these transistors is equal to infinity, so we can neglect the resistance looking into the drain. And in this case, our voltage gain is equal to minus GM1 divided by 1 plus GM1 times RS1 times RD1 times GM2 divided by 1 plus GM2 RS2 times RS2. Now the voltage gain in this case is equal to the gain of the first stage minus 0.97 volts per volt times the gain of the second stage, 0.94 volts per volt, or about 0.91 volts per volt. Now interestingly, we know that the gain of the common drain stage should be a little bit less than unity. We normally expect the gain from our common source stage to be a little bit higher than unity or higher than unity. But in this case, the values of RD1 and RS1 are similar, which makes the gain very similar. Now, in this case, it also asks us to find the small signal output resistance. This is the resistance looking in this direction. Now we know when we look into the source of a transistor, we see approximately 1 over GM of the transistor. And this is going to be in parallel with RS2. This is 185 ohms in parallel with 3 kiloohms. Now, off the bat, I might automatically say that 185 kiloohms is so small that it being in parallel with such a large value of 3 kiloohms is just going to be approximately equal to 185 kiloohms. Of course, if you carry out the calculation, you'd actually find the value of this is 174 ohms. All right, so that concludes this example problem.